All right, in this section we're going to look at basic trigonometric forms. The idea here is the same as in the other sections that we've already looked at. We want to use a u substitution if needed to make our integral fit one of the integration formulas we have. So we have a bunch of these basic trig forms, and they all come from, with the exception of these last two, formulas 1 through 6, come from the derivative formulas we already know. The derivative of sine is cosine, and that gives us the formula for the second, the integral of cosine is sine. The derivative of cosine is negative sine, so the integral of sine is negative cosine. And down the line. Formula 7 and 8 do not come from basic derivative formulas that we already know, but you could convince yourself that these formulas are true if you take the derivative of, say, ln of secant plus tan. You'll see that you do in fact get secant u. Sometimes, in addition to finding the right substitution, sometimes we need to use some trig identities to help us rewrite. So, generally our rules, our tools are u substitution and algebra. Now we're going to add to that, sometimes we'll need to use a trig identity. We'll start with this example, the integral of x times secant squared of x squared dx. And if we're looking for a u substitution, there's, I hope, some comfort in knowing that at least there's a finite number of choices we have as we scan this function. In any integral, there's a finite number of choices you could pick for u. So, you kind of hope, like, well, eventually I might stumble upon the right one. Just note, though, in all of these basic trig forms, u is the argument or angle inside the trig functions. So if something fits a trig form, you're going to let u equal the argument inside. So here, I'm going to let u equal x squared. Then du is 2x dx. I need an x already there, and we have that. We're off by a factor of 2, which does not bother us because we could put in a factor of 2. Now we have this part is secant squared u, and this part is du. So we have secant squared u du. The function whose derivative is equal to secant squared, well, that's the tangent function. Whoops, I've already integrated, so I'm not going to write the integral sign. 1/2 tan u plus a constant. Putting our expression for u back in, we get 1/2 tan of x squared plus a constant. And you can check, if you take the derivative of 1/2 tan of x squared, you will get secant squared of x squared times x dx. Okay. In example 712, we've got cotan 2x over sine 2x. Now, immediately, there's nothing that shows up where I say, oh, here's u, and I see its derivative show up somewhere else. The derivative of sine isn't cotan, it's cosine, so it's not going to be that. It's not a log form. So what I'm going to do is just rewrite this a little bit. Instead of a sine in the bottom, I'm going to bring that up. Remember that 1 over sine is cosecant. So if I have a sine 2x in the bottom, I could bring that up and it'll be a cosecant 2x. So I got cosecant 2x, cotan 2x dx. Now, if you think you recognize it, go ahead and pause the video, try to work it out. But cosecant cotan, that's a form we know, that we kind of already know, right? We're seeing it now as an integral form, but we already know of a function whose derivative is cosecant cotan, and that is the negative cosecant function. So, and that leads us to this formula right here. So that's what we're going to use. You should be in the habit of being able to, with enough practice, so that you don't need to refer to formulas 1 through 6. Formula 7 and 8 will always be provided for you, and yes, when you take this test, you can make a note card, so you can put whatever formulas on it that you want. But these first 6 formulas come from derivatives that we already know. So with enough practice, I think you probably won't even need to rely on referring to those formulas. So I'm going to let u equal 2x. Again, if it fits a trig form, u is the argument inside the trig function. And one good sign here is that to begin with, the arguments were the same. They matched up, and that's always a good sign. So du is 2 dx. I need a factor of 2. I'm going to throw that in. Compensate outside. Now we have cosecant u, cotan u, du. There's our du. And the integral of cosecant cotan is negative cosecant. So we get negative 1/2 cosecant u plus a constant. Going to throw in the expression for u, which is 2x. So negative 1/2 cosecant 2x plus a constant. Okay, in the next one, we have sine 2x over cosine squared x. So be really careful. The first thing that grabs my eye when I see this is that the arguments are not the same. The arguments don't match, and that's a sign that we might need to use a trig identity. To help us rewrite it. The double angle formula for sine tells us that sine 2x is equal to 2 sine x cosine x. So my first step is I'm just going to rewrite this integral, replacing sine 2x with 2 sine x cosine x over cosine squared x dx. I'm going to yank out this 2, bring it outside, and also I'm going to cancel. I've got a factor of cosine on top, and I have a cosine squared in the bottom, so that'll cancel, and then we're left with just a single factor of cosine in the bottom. So we have 2 times the integral sine x over cosine x dx. So sine x over cosine x, that is equal to tan x, and you might see a formula given for the integral of tan x, but we don't need a special formula for tan x, and you'll see it's actually not given in the page of formulas a page ago. We just need to make a substitution, and recall, if you think you have it or you want to give it a try, pause the video. But recall that the derivative of cosine is negative sine, so I'm going to let u equal cosine x. And then du is negative sine x dx. The reason I didn't pick u equals sine x is because du should never be in the bottom. We don't want that du function to be in the denominator of a fraction. So du is negative sine x dx, so I just need a negative here. I'm going to throw that in. It's a factor of negative 1. I'm going to compensate outside. So now we have minus 2 integral du over u. This is, in fact, a log form. So we know how this goes. The integral of du over u is ln of absolute u. So we have negative 2 ln of absolute u plus a constant. And now I'm going to plug our expression for u back in. Minus 2 ln absolute cosine x plus a constant. Okay, let's try another one. Sometimes it might take a few tries to get the right substitution. We have a lot of choices. We have a tan theta, we have a cosine theta. Cosine theta stuffed inside a ln function. And it probably won't surprise you to learn that the first thing I'm going to just drag out that factor of 5. I feel like it kind of just crowds things and makes it harder for me to see what I need. So I've got the integral of tan theta times ln of cosine theta d theta. Okay. You know, you might try a few different things. Go ahead and pause the video if you want to give it a go. It might, you know, this is a really good example of where it sometimes takes us a few tries to get the right substitution. But the derivative of tangent is secant squared, and I don't see a secant squared anywhere, so I'm not going to pick that. The derivative of cosine is negative sine, and I guess you could say we do sort of have a cosine, or a factor of sine inside the tan function. Tangent is sine over cosine. But that would have cosine, that would have our u stuffed inside a ln function. And we should note that we have no formula for ln of u. The log form is so named because the result is log, not because we're integrating the log function. So I'm going to let u equal the ln function, ln of cosine theta. And then taking the derivative, du will be 1 over cosine theta times negative sine theta d theta, or simplifying this, du is a negative tan theta d theta. So there we go. We have our du showing up. We're just off by a factor of -1. I'm going to throw that in, compensate outside, and now let's see what we got. If u is ln of cosine theta, then this is our u, and this piece here, that's our du. So this is the -5 times the integral of u du. This is a power rule integral. So one of the things you're going to get used to is as you go through the exercises, they might mix up these forms. You know, you might be doing exercises that are about the trig forms, but maybe it just ends up being a power rule integral, right? We have to see what it looks like after we make a substitution. We're trying to get the integral to reveal its form to us. So this is u to the first, and applying the power rule, we get 1/2 u squared plus a constant. And now I'm going to just clean it up and put our expression for u back in, so we get -5/2 times ln of cosine theta squared plus a constant. It's important to note we're squaring the whole ln function, we're not squaring the argument. So I cannot use that property that says I could pull a power down in front of the ln. That's only true if we're raising the argument inside the ln to a power. I'm going to, you know, probably just leave it like this, but it's also pretty common when you're squaring the ln function to write it like this, ln squared of cosine theta. Kind of like we do if we're squaring the sine function, we call it sine squared of theta. Okay, one more. Go ahead and pause it if you want to try and see if you can't pick a good u substitution here. We're looking for something we could pick for u where we see its derivative show up somewhere else. Looking at this, the thing that stands out to me is that the derivative of tan is secant squared, but I don't want to have an x plus u in the bottom. Like when we make a substitution, we go from an integral that has just x's to an integral that has just u's. We don't want to mix them together. It's hard to know what to do with x plus u. So, but remember that the derivative of x is of course 1, so I'm going to let u equal x plus tan x. And then du is 1 plus secant squared x dx. And when we make that substitution, we don't even have to put in any constants, right? Like this is u, and this is du. So this really just straight out of the gate, when we make that substitution, we get du over u. This is a log form, natural log of absolute u plus a constant. and just putting our expression for u back in, natural log of absolute x plus tan x plus a constant.